All right, so the other day we were looking at the periodic table and we saw that as you go down a column, you run into elements that have really similar reactivity. And that's how Dmitry Medalev organized our periodic table that we have today. So if we look at the periodic table, it looks a bit like this. Sometimes they're color-coded, sometimes they're not. It doesn't really matter. In this case, it's color-coded to show the different element types. We'll talk more about this later, but for example, the ones we saw yesterday were in this column. I guess it was Tuesday. These were called the alkali metals. These are really reactive when you put them in water. The next ones in this column, so that tan column, are the alkaline earth metals. We'll talk more about those. The ones in the middle here are called transition metals. And then we've got a lot of organic compounds over here. These are called post-transition metals. These are halogens, and then these are noble gases. I don't expect you to memorize all of these right now, but the idea being that if you stack things in a column, they tend to have similar reactivity, with the exception of the far right-hand side. You can kind of see almost a stair step. They do change a bit where you're dealing with slightly different physical properties. Yep.
In the case of the transition metals, is like for grouping properties, is it more important to look at the columns or as them as a whole? Like how much is it varied throughout the transition metals?
That's a good question. So the question was, is it more important to think of them as being grouped into a color-coded region or look up and down a column? Look up and down a column. Those are going to have the most similar reactivity. Yep. All right, so there's a lot of information that's presented in the periodic table. It can be a bit overwhelming to look at, but let's break it down, and I'll show you an example. Ooh. And in this example, we're going to take one element from the periodic table. This is Fe. If you look at the periodic table, it is number 26. So it'll have some number typically right above. I see it over there. It's kind of smack dab in the middle. All right? And then under that, sometimes you'll see a chemical name. Does anybody know what the chemical name is for Fe? Iron. Does anybody know why it's Fe and not IR? What do you think?
It was originally ferrous.
Yeah, exactly. So oftentimes these are derived from their Greek or Latin names. So ferrous is the Greek term for iron. IR is actually iridium, so be very careful with the initials that you use. The big thing to remember is with elements, you always, always, always capitalize the first letter. You never capitalize the second letter after it. So we've got Fe for iron, and then below that you'll typically see a number that's 55.847. That's for iron. So this would be a pretty standard symbol on the periodic table for iron. Sometimes you'll see more, but this is the most generic. So like I said, the first number is always going to be your atomic number. That never changes. Fe is your element symbol. Down here we have the English name. And then down here, does anybody know what this number is? Somebody else? Mass, exactly. So this tells you the average atomic mass. Atomic mass. And the units for this are a little bit weird. They don't measure this in grams because it's such a tiny, tiny, tiny number. Instead, this is called the atomic mass units, or AMU. So let me zoom out here. So atomic mass unit. And we can actually convert between atomic mass unit and grams, so I'll show you what that conversion is. So we'll do AMU. Like I said, is atomic mass unit. And 1 AMU is equal to 1.6605 times 10 to the negative 24 grams. So this is an incredibly small mass. We switch it to AMUs just so we've got easier numbers to work with. It's easier to deal with numbers that, you know, are in that 0 to 100, 200 ballpark. Yep.
Where does the AMU come from? Is it like the atomic mass of, I don't know, hydrogen?
Yeah, that's a good question. So where does AMU come from? It gets a bit complicated, but there's an element called carbon-12. And we'll talk more about this later, but essentially carbon-12 has exactly 6 neutrons. We haven't really talked about what a neutron is yet, but carbon-12, by definition, is exactly 12 AMU. So that's how everything is based off of, is its relationship in mass to the mass of a carbon-12 atom. Yep, good question. All right, so let's do some unit conversions here. Let's do a practice one. I think we did one similar earlier. How much does Batman weigh? Actually, I should be saying what is the mass of Batman, but we'll stick with this in AMU. And we'll say that Batman is a pretty big guy. It's about 95 kilograms. So I'll give you a minute to work on this, but make sure you're setting up your unit conversion correctly. And do we need any other? All right, so let's try to do this as a class. So we need some unit conversions. The first one I already gave you. I said that 1 AMU is 1.6605 times 10 to the negative 24th grams. So we're able to switch from grams to AMU, but we can't switch directly from kilograms to AMU using this conversion, right? So now I'd say, all right, 1 kilogram is equal to some amount of grams. And if you remember, kilo stands for what? It's 1,000 or 10 to the third. So I'll go ahead and write 10 to the third grams. The big thing is keeping that 10 to the third on the opposite side of the prefix, right? Because the prefix K is equal to this. Okay, so we've got our 2 unit conversions. We could say, all right, 95 kilograms. We want to cancel out kilograms, so I'll put it on the bottom. We can convert that to grams using our unit conversion right here. And we could say for every 1 kilogram, we have 10 to the third grams. Now we've canceled out kilograms. And now we want to go from grams to AMU. So I'll put grams on the bottom and AMU on the top. Let me slide this over. And we know for every 1 AMU, we have 1.6605. I might have to slide this over. Times 10 to the negative 24th grams. Now we've canceled out grams, and we're left with units and AMU. When I type this in, I get 5.721168323 times 10 to the 28th AMU. Is that my final answer? Nope. 2 sig figs are going in. That means 2 sig figs should come out. So in this situation, we would say 5.7 times 10 to the 28th AMU. A completely absurdly large number, which is why we prefer measuring things in kilograms or grams. Does that make sense? Yeah?
Should we capitalize the AMU?
That's a good question. It can be lowercase. I actually don't remember if it's supposed to be capitalized or not. Yeah, I think it's lowercase, so I might have done capitalized incorrectly. All right, so going back to that carbon-12 example, It's a little bit confusing when you see the atomic mass on the periodic table and what that represents. So like I said, one atom of carbon-12 is exactly 12 AMU. So what you see on the periodic table is an average. It's not an exact mass. And what I mean by that is if we take carbon-12, we know that's exactly 12 AMU. Carbon-12 makes up 99% of all of the carbon on our planet. However, we do have some carbon-13. Carbon-13 is just like carbon-12, but it has one extra neutron, and we'll talk about what neutrons are, but neutrons do have a little bit of mass, so this is a bit heavier. This makes up about 1% of all the carbon on our planet. And we also have another type of carbon called carbon-14. Carbon-14, there's a really, really, really small amount, so we just say trace. Does anybody know what carbon-14 is used for? I'm just trying not to call you every single time. It's okay. Anybody else? Think about archaeology or digging up dinosaur bones. How do they date them? Carbon dating, exactly. So when you do carbon dating, what you're really looking at is how much carbon-14 is still present in a given sample. It decays slowly over time in a predictable way, so we can actually do some math to figure out how old samples are when we dig them up by looking at carbon-14. So the mass that's listed on the periodic table is an average of all of these combined together. So the AMU listed is the average of all isotopes. And we'll talk more about what it means to be an isotope, but the general idea is they differ in the number of neutrons that they have. Yep.
Is the average weighted by how prevalent that isotope is on our planet?
Yes, absolutely. So the question was, is the average weighted by the percentage of a given isotope? Definitely. So the average is more heavily weighted towards carbon-12 than carbon-13, and then carbon-14 really doesn't play a big role in the average. Yep. All right, so we've thrown out a lot of new terms, specifically neutrons, isotopes, things like that. So we're going to take a step back and then start describing what's going on inside of an atom. And that's where chapter 3 begins. And there were a bunch of experiments done in kind of the late 1800s, early 1900s, where they were trying to figure out what the heck's going on inside of an atom. It happened pretty rapidly. The first one was done by a guy named J.J. Thomson, an English chemist. And you can actually read his quote here. He says that if in the very intense electric field in the neighborhood of the cathode, meaning one side of a battery, the molecules of a gas are dissociated and split up, not into ordinary atoms, but into those primordial atoms, which we shall for brevity call corpuscles. He was just making up words at this point. All right, so he called these new things that he was looking at corpuscles, and he said if these corpuscles are charged with electricity and projected from the cathode by the electric field, they would behave exactly like cathode rays. So it's kind of confusing, but let's take a look at this video. Do you mind flipping the lights? And he invented something called a cathode ray tube. Or I shouldn't say invented it, he was the first to use it.
Okay, this is a cathode ray tube. What it essentially is, it's a vacuum chamber. There are no gases inside this glass tube. The only thing we have are two electrodes, one's called the cathode, the other's called the anode, and a fluorescent screen in the background. It's coated with some type of fluorescent material. When I turn the power supply on, we'll see a beam that causes that fluorescent screen to glow. Looks like a nice straight line, doesn't it? We call that a cathode ray because it emanates or begins at the cathode and shoots across over to the anode. J.J. Thomson was working with cathode rays. We really didn't understand what they were. I mean, we have electricity going in one side and coming out the other, but there's nothing inside to conduct it. It's a vacuum tube. So he decided to apply a magnetic field to this cathode ray. and he found something interesting. Let me apply one pole of the magnet to this beam, and we'll see what it does, and then we'll flip it around and see what the other pole does. This is my favorite part. Can you see what's happening to that beam? What does it appear as though it's happening to it?
It's moving.
It's moving. It's being repelled, isn't it, by the magnet? Let me flip the magnet around, and what do you think is going to happen this time? Well, if it's being attracted on one pole, see how it's being attracted there? Let me rotate it so the kids on this side of the room can see it. See how it's being attracted there? And then the other pole, do you see how it's being pushed down? What does that tell me about that beam? It has a what? It has a charge. Let me tell you about the poles of the magnet. The one that pushes it away is the negative pole. So what does that tell you about the charge of those particles? Negatively charged particles. And J.J. Thomson was actually able to do a charge to mass ratio of these particles, and he found that these particles were about 2,000 times lighter than a hydrogen atom. Now at the time that was very profound. What did Dalton say? Are there any particles smaller than an atom? J.J. Thomson just found something 2,000 times smaller than a hydrogen atom. Why is the hydrogen atom and something 2,000 times smaller than it so profound?
Hydrogen.
Because hydrogen's the smallest atom, isn't it? So if we found something 2,000 times smaller, we have found our first subatomic particle.
All right.
It's called the...
That's where we'll stop. Do you mind turning the lights on? How many of you are familiar with the old TVs, the big ones, not the flat ones that we use today? Those were actually cathode ray tubes, right? So they call them CRT TVs. It actually uses the same technology. You apply an electric field, you can excite a gas, and then that gas, in this case, is called Corpuscles by J.J. Thomson, and we know that they're not true atoms anymore. They're something that's negatively charged. All right, does anybody know what the subatomic particle is that's negatively charged? It's an electron. So he was the first to describe an electron. And like they said on the video, it's smaller than hydrogen. That's a key thing that he discovered. And so it was referred to as a subatomic particle. Luckily, the name corpuscle never caught on. They switched it to electron later. All right? This then brought out an interesting debate about where those electrons are in an atom. And there were two competing theories. So let's take a look at J.J. Thomson's theory. He wasn't entirely sure where these electrons were located, but what he imagined was that you've got this atom that's floating around, and inside this atom you've just got a bunch of electrons floating around, and that there must be some blob of positive energy in there to bounce out the electrons, right? If the electrons are negative, there must be a counterpart that's positive. He didn't know where the positive thing was. He just said it's this big blobby area, and he didn't quite know how to describe it, and he called this plum pudding. I don't know if anybody's ever had plum pudding, but essentially it's a bread with a bunch of like fruits in it, specifically plums or raisins. And so he imagined the electrons being like the raisins in that bread. All right, he had a student that said that's stupid, and his name was Ernest Rutherford. And he was convinced that this was not the case after doing some experiments. And instead, he said, no, there's actually something inside of the atom that's kind of dense. And then the electrons are around that. And he said that this thing inside of the atom is a nucleus, similar to cells having a nucleus, right? But atoms, in this case, he said, must have a nucleus. And he said that the nucleus must be positively charged. So it must be positive. dense, and it doesn't take up much space. I kind of have it exaggerated here, but this is essentially what he was describing. And he did a really cool experiment involving gold foil. I don't know if you know much about gold, but gold can actually be hammered out into only a few hundred atoms thick. So you can keep on hammering gold until it gets thinner, 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 until it's only a few hundred atoms. That's why they put it on like decorations. There's not really that much gold in gold foil, therefore you're not wasting a lot of an expensive resource. And then what he did was he got a radioactive source called an alpha source. And an alpha source is kind of interesting. It is helium atoms without their electrons. So those are referred to today as alpha particles. And he could get a beam of these focused, fire them at gold foil. And then what he expected from J.J. Thomson's thing was that electrons are super duper tiny. Most, if not all, of the rays should go entirely straight through, right? Because there's not much matter inside of an atom. But what he saw was that pretty frequently, these helium atoms without their electrons were being deflected to a really large degree. That could only make sense if you had something in there that was really dense and that didn't take up much space. If it took up a lot of space, you'd expect a lot of deflection. If it was pretty small, you wouldn't observe very many deflections. So a better way of viewing this is kind of like this, where we've got these circles representing atoms. Each of these red dots is the nucleus. And then you've got an alpha source of helium particles being blasted at it. Most of them go straight through, but sometimes these helium atoms without their electrons will hit the nucleus of one of these atoms and get deflected at various angles. And so it's pretty interesting. Do you want to turn the light off again? All right, so he fired these alpha particles. Most of them went through. I won't show you this video, but he actually had a fluorescent screen on the back, and so he could see them light up every time they were deflected. I really like this video down here. Has anybody heard of Crash Course? He does a lot of good videos. He has a good way of describing all of this too, so you're welcome to watch this video on your own time, but he kind of breaks it down and makes it more fun. All right, then there was one last experiment. Like they said, J.J. Thomson said the mass of an electron was about 2,000 times smaller than a hydrogen atom. Robert Millikan even went one step further and was able to describe its almost perfect mass. We still use that mass today, give or take a few units. And so he did an experiment called the oil drop experiment, where if you take physics, you'll actually talk about that in more detail. So he found the exact mass of an electron. So there's a lot of unique history here, and it all happened from the span of about 1897 to about 1909. So it was a pretty fruitful period in chemistry. A lot of new stuff was discovered. All right, do you want to turn the lights back on? I think we'll skip these videos. Okay, and so let's start to describe these subatomic particles. The first one was an electron. We said that the charge of an electron was negative. Specifically, they called it -1, so every electron was a -1 charge. The mass of an electron is roughly 2,000 times lighter, but more specifically, it was 1/1837. So it's very, very tiny, and this is AMU for our atomic mass unit. So it's almost 1/2000th of an atomic mass unit. And like Ernest Rutherford said, he said the location is outside the nucleus. So pretty important discovery. The next ones are going to make up our nucleus. The nucleus, it wasn't well understood what it was made up of. We knew it was positive to counteract the negative charge of electrons, but it was later discovered that there were some neutral particles in there called neutrons. Neutrons are neutral. They don't have a charge, so we just say 0. The atomic mass unit is 1, and it makes up a part of the nucleus. Like I said with carbon, we can have carbon with different numbers of neutrons in there, but it doesn't really change the atom very much because it doesn't have a charge to it. All right, and then last but not least, we've got protons. Protons have a positive charge. They're also 1 AMU, and they make up the other part of the nucleus. Okay, and like I said before, you can have isotopes. We talked about that with isotopic dating of carbon. We said that atoms or elements can differ in the number of neutrons. They contain. So I'll show you another example of this. We've got an atom with 1 proton, so I'll indicate that that's positive with a circle around that. If you look at the periodic table, it's actually pretty handy. The atomic number always equals the number of protons. So if we look at it, this must represent hydrogen. So in a normal hydrogen atom, you've got 1 electron just kind of zipping around in a cloud around that proton. So to show this, we show it by indicating that the mass of the nucleus is 1 for this hydrogen atom. All right, however, there are other hydrogen atoms where you have not only a proton, but you also have a neutron, and you have an electron zipping around it. Like I said, hydrogen is always defined by the number of protons it contains. So in this case, it still has 1 proton, but we've added a new subatomic particle, the neutron. And the mass of the nucleus in this case is going to be 2. And then last but not least, we've got one form of hydrogen where it has 1 proton and 2 neutrons with an electron zipping around it. And you can imagine that the mass of the nucleus is going to be 3. So you can indicate that with the superscript 3 that comes before the element symbol. It is a little bit confusing. All right. So what you can do in addition to that is indicate the atomic number right below. Just one second. So you could say, all right, this is always a hydrogen atom. Atomic number of hydrogens always going to be 1. Sometimes you see it this way where you have a 1 indicated. Other times you don't have it shown because the symbol tells you the atomic number anyway. So it's kind of optional to include that. So let's make some notes here. Then I'll come back to your question. The number in the top left-hand corner is always going to be the number of protons plus neutrons, where the number on the bottom is going to be the number of protons only. And like I said, this is the same as your atomic number. So all of these are described as isotopes because they differ in the number of neutrons that they contain. The first one, when you have no neutrons in the hydrogen atom, is just called hydrogen. The next one is called deuterium. The next one is called tritium. Tritium is really radioactive. Typically, the more neutrons you force in there, the less stable the atom is, and it wants to fall apart through radioactive decay. What was your question?
I know that most atoms don't just have like their atomic number of protons and no neutrons. But you said neutrons were neutral. Are they exerting some other force that keeps the atom together?
Yeah, so the question was kind of what's the purpose of a neutron in there if it has no charge? There's a nuclear force called the strong nuclear force. We're not really going to get into that. It becomes really important when you start talking about things like atomic bombs and stuff like that. There's a huge amount of energy in there. We're just not going to get into that in this class. Yep. All right. So we've got all of these different elements. One of the questions on the pod, essentially I give you these two numbers, and I want you to tell me, all right, is this, for example, hydrogen 1? Is it hydrogen 2? Is it hydrogen 3? So let's take an example of that. Let's say from the periodic table, I'm just going to pick one. Let's do 39 here and 19 down here. And the element is going to be some unknown element X. What is unknown element X going to be? What's the symbol? K. Does anybody know what K stands for? Potassium. So this would be potassium. And in this case, we want to indicate what isotope of potassium we're dealing with. So what number should come after it? 39. So that indicates the mass of your nucleus. So you'd say, all right, this is a potassium 39 atom that we're referring to here. So alternatively, we could rewrite this using the element symbol. And like I said, sometimes you'll see that 19 written, but if the K is written already, it implies that that's 19, so it's kind of optional there. All right, so let's make a couple notes. An atom, or element, is defined by the number of protons it contains. An isotope has the same number of protons but a different number of neutrons. All right. So I was going to show you a cool element, one of my favorite ones. Right here is kind of this red block. It's a little bit hard to see, but it's essentially glowing red hot on its own. There's no heat source being applied to it. It just naturally is super duper hot on its own. This is called plutonium-238. This isn't the plutonium that's used in atomic bombs. The plutonium that's used in atomic bombs is a different isotope, right? So it has a different mass number in its nucleus. Plutonium-238 is really interesting. Has anybody read the book The Martian or seen the movie? So in that movie, he goes out to one of the rovers and actually steals the plutonium-238 on the inside. And why did he do that?
Stay warm in the vehicle.
Yeah, stay warm in the vehicle. This thing stays really hot. And then the other thing he needed it for, too, was a power source. So what NASA does is, let's say you send a probe way out past Jupiter. There's not enough sunlight out there to have solar panels to run all of the instruments that you need. Instead, they get a brick of this, they throw it on the inside, and then they convert the heat energy to electric energy, and this will stay red hot for decades and decades and decades. It has slow radioactive decay. In fact, if you're familiar with the Voyager probes have a ton of this stuff on the inside, and they've been sending us information back since the 1970s. The interesting thing, though, is this doesn't last forever. It decays slowly. So the Voyager probes, they've slowly had to turn off instruments one after another because they don't have enough electricity being produced. All right, so my first question is, what are the number of protons in this element? And then number two, what is the number of neutrons And then number 3, what is the number of electrons? And assume that there's no charge, so this isn't a positive or a negative element. Does anybody think they got all 3? Not yet. Let's not overanalyze this. What's the number of protons that plutonium always has? 94, because it's defined by having 94 protons. So that one's pretty easy. All right, what about neutrons? How can we figure that out? Subtraction, right? So again, not super hard. Go 238. That's the mass number of the nucleus. Subtract out the number of protons that you have in the nucleus, and you're left over with 144 neutrons. All right. We know protons are positive. Has to be balanced out with a negative charge. So how many electrons must we have? 94, exactly. All right, so that's where we're going to end off today. Tomorrow, we'll come back in and we'll do more practice with looking at subatomic particles.